Hey, in this video we're going to talk about variation of parameters. And you might be saying, if you've been keeping up with my other videos, haven't we done this a billion times? And yeah, we've been using the method of variation of parameters to some extent, but we haven't really approached it in all of its glory, right? We haven't seen the full scope of what it can do. So in this chapter, it's devoted to variation of parameters, and we're going to put it to full use. Okay, so let's take a look. All right, so variation of parameters. I have a differential equation set up here. This is the form that we're going to be looking at. It's going to be some function times y double prime plus some function times y prime plus some function times y equals some function. So these are functions of x. We're going to assume that this function here, p0, does not have any zeros on some interval where we're looking for our solution. The reason for that is that we usually like to divide through by this. And if you divide through by something that has a zero, things can get a little bit mucked up. And if you know about the uniqueness and existence theorem, we know that that's also a problem point, right? So that's the setup here. These are functions. This one doesn't have any zeros in the interval where we're looking for our solution. Okay, so the idea here is that we are going to we want to find a solution, and suppose we know that y1 and y2 are two solutions to the complementary equation. All right, so suppose y1 and y2 solve the complementary equation. That's the equation where you take the right-hand side to be 0. Okay? Now, what we're going to do is we're going to form our particular solution based on those two. Okay? So we're going to take our particular solution to be some function times y1 plus some other function times y2. Notice this is a little bit different than what we've done before. We only looked at it one at a time, right? But this is going to give us another way to go about things, okay? So if I do this, I want to be able to check to see if it satisfies the differential equation. So what I'm going to do is take some derivatives and check what happens when I plug it in. So I'll take some derivatives of y, the particular solution, right? So let's get these. Okay, I've taken the derivative. That's fine. I'm going to take a second derivative, but before I do that, we're going to put an assumption on these functions, okay? We're going to see if we can get away with restricting what these functions can be, okay? Because if we can restrict them and still get away with it, that's great, because then we'll have some simpler functions we'll be dealing with, okay? And the restriction that we're going to use is we're going to require that this piece here plus this piece here is equal to 0. Now, it might seem weird to you, like, why can we even get away with this? But, you know, it's okay. If we can prove that we can get away with it, then it's fine. So we'll try it and see if it works. Okay, so we're going to assume at this point, assume that our functions u1 and u2 are chosen such that this is equal to 0. Okay, so these two pieces, therefore, are gone. Let's see if we can get away with this, all right? It's okay to try things like this. If he don't get away with it, then you try something else, right? You just go with general functions. But let's see if this works. Then when I do y double prime, I've only got these two pieces to worry about. So I'm going to get... okay. Now what I'm going to do is I'm going to plug these guys into this differential equation up there. Okay? Okay, now what I'm going to do is I'm going to collect the u1s together and the u2s together. Okay? And this whole thing here is just equal to f. Now, what do we know about y1 and y2? Well, these are complementary solutions, right? They solve the complementary equations, which means that this piece is 0 and this piece is 0. So really, all that we have left here is this guy, okay? So that's the equation we're going to be looking at. Now, what I'm going to do here, we're going to put this together with our other equation. I'm going to write it down as a system, okay? So what was that one equations that we started with? Well, we made this assumption. So I'm going to write this down, and I'm going to write this new equation down, okay? So let's write these down together. Where I've divided both sides by p0 over here. Okay, so now we have a system of two equations. Okay, so what we want to do is we want to see if we can solve this for u1 prime and u2 prime. Okay, so what we're going to do here, I'm going to multiply the top equation by y2 prime and the bottom equation by y2. Okay, let's just go ahead and do that and see what we get. Okay, I get this. Now, some things match up. If I subtract the top equation, let's subtract the bottom equation from the top equation, okay, you'll notice that these terms cancel off over here, okay? So then I'm going to have this piece minus that piece, and I can factor out the u1 prime, okay? So that's what I'm going to do. Okay. Now, I want to solve this for u1 prime. So what I'm going to do is I'm going to divide both sides by this guy. Okay? Now, that will make sense only provided that this has no zeros. Okay? If this has a 0, then I might run into trouble. So what we want to do next is we want to verify that this thing actually won't have any zeros. And that's what we're going to do next. So I'm going to go to a new sheet, and we're going to do that, and then we're going to come back to this, okay? All right, so here's our claim. This thing has no zeros, okay? Now, by the way, this thing, I'm going to call it W, okay? And by the way, its name W comes from what we call it. We call it the Wronskian. This is called the Wronskian. When you have two functions and you do this to them, that's called their Wronskian. Okay, and remember, where did these functions come from? These were solutions to the complementary equation. All right, that was this differential equation. And remember that P0 had no zeros, so I can divide through by P0. When I divide through by P0, these become new functions. I'm going to call them lowercase p and lowercase q. Okay. Now what I'm going to do is, so let me just point out, like I said, y1 and y2 are solutions. Are solutions to this differential equation. It's the same differential equation, just written two different ways. y1 and y2 are solutions. Okay. Now what I'm going to do is I'm going to take the Wronskian and I'm going to take the derivative. Okay. Let's differentiate the Wronskian and see what we get. All right. So just differentiating this thing. Okay. Well, I see a couple of things are the same. These cancel. Okay. Now, what can I do here? Well, look at this. y2 double prime solves this differential equation. So I can solve this for y2 double prime. Just put y2 double prime in here for y, solve it. And what happens here? Well, we get a y1 times that stuff, right? But we've put it on the other side of the equal sign. So I guess a negative comes out and I get this. Okay, and y1 solves this differential equation. So if I plug y1 in here, I can solve it for y1 double prime and replace y1 double prime with that thing. Right. Oh, no, it's not equal to 0. Sorry. It's getting late. I'm making mistakes. Okay, so ignore that. It's not equal to 0. It's just this thing, this stuff is equal to this because I made that substitution and plugged it in. Okay? So, all right, what can we do now? Well, okay, so what we're going to do is we're going to collect the p terms and the q terms separately. All right, so let's get all the p terms on the left. And I'll put all the q terms over here off to the right-hand side. We'll just separate these terms, okay? So let's see what I got here. Okay, I got this. But look at this. This stuff, this plus this is 0. They're the same, right? So they cancel out. So this whole thing is gone. Okay, so I'm just left with this guy. Now what is this? Look familiar? That's W. That's the Wronskian. It has reappeared. All right? So it has reappeared. So I really have P times W. So look at this. I got a new differential equation. W prime equals P times W. I wonder what the solution is. Well, that's easy to solve, right? It's separable. When we solve this differential equation, what do we get? We get W equals a constant times e to the negative integral of this function with respect to x. Remember, p is a function. But yeah, if you go ahead and check it, plug this in for w, you see its derivative is equal to, I'm missing a minus sign here, right? Because this is actually negative of the Wronskian. Sorry, I missed that. If you compare that to the Wronskian, they're actually negatives of one another. Notice. I think. Yeah, this is. Yes, they're actually negatives of one another. So, yeah, I forgot the minus sign. So this is actually the solution to this differential equation right here, right? Okay, now there are two possibilities. Either c is equal to 0, this constant, or c is not equal to 0, right? Well, if c is equal to 0, that means that the Wronskian is just identically 0. Okay? Well, if the Wronskian is identically 0, that means that, let me go up here, that means that y1, y2 prime minus y1 prime, y2 is equal to 0. Well, look at this. We can separate these. I can add this to both sides. I can get all the y1s together and all the y2s together, right? And when I do that, what do I get? I get y2 prime over y2 equals y1 prime over y1. Okay? And I can anti-differentiate both sides. I get the natural log of y2 equals the natural log of y1 plus a constant, just by anti-differentiating. And then I can take the exponential function of each side. And I see that y2 has to equal some constant times y1. Okay, well, what's the issue with this? Well, when we choose y1 and y2, we always want to choose them to be a linear independent set of solutions, right? So if we can do that, then this is impossible. Okay, so this is impossible if y1 and y2 are independent. Okay? So if we choose y1 and y2 to be independent, none of this is possible. And so we are stuck going to this case, where c0 is not equal to 0. Okay? Now, what is true about this road? Well, if c is not 0, we have it's multiplied by this function, e to the something. Well, e to the something can never be 0 either. So that means that w is never equal to 0 for all x. Okay, this is what we were trying to show. This guy, what we were calling the Wronskian, has no zeros. So if we choose our y1 and y2 to be independent, then this thing is guaranteed not to have any zeros. Okay, so let's go back to the problem. Okay, so here we are. This is where we were. This thing, remember, is w. Right? And we said it had no zeros if we choose y1 and y2 to be independent solutions to the complementary equation. We can divide both sides by w. And then we have an equation for u1 prime. Okay, so let's do that. All right, so u1 prime is equal to this. Okay? In the same way, you can do the same thing that we did for u1, you can do it for u2. All right? So I'll leave that as an exercise for you, and you can check this. Let me check it just to be sure. Yeah, it looks just like this. So we got an equation for u1, an equation for u2, and you can solve these, right, by just anti-differentiating the right-hand side. And so we can find u1 and u2, which will give us our particular solution, all right? And that's what we're after, okay? So let's do an example problem, okay? Okay, we want to find a particular solution of this differential equation given that x and e to the x are solutions to the complementary equation. That's what you get when you set this equal to 0. Then find the general solution. Okay? So, what did we say here? We said that we are going to take our particular solution to be u1 times y1 plus u2 y2. Okay? Nope, I forgot my subscript 2 there. Okay. And what we had, if you recall, was a system of equations that we needed to solve. Okay, this is the system. This first thing was the assumption that we were going to make, right? And then this one was the thing that we derived based on that assumption. Okay? So we're going to write this down. Okay? So I'm going to have this system. I know I have u1 prime times y1, which is x, u2 prime times y2, which is e to the x, and that's equal to 0. And then I'm going to have u1 prime times y1 prime, which is just 1, and then u2 prime times y2 prime, which is just e to the x again. And that thing was equal to the right-hand side. Oops. I can't keep track of where my stuff is. The function divided by p0, all right? So it's going to be this thing divided by that thing. Well, that's just x minus 1, okay? So there we go. This is a system of equations we need to solve. All right, let's see. How can we solve this? Let's subtract the top equation from the second one, because I see I'm going to get a 1 minus x here, which looks a lot like this x minus 1. Okay, so let's subtract the top equation from the bottom equation. So you're going to have this, right? Because these two things cancel off, and so what does that tell us? It tells us that u1 prime is equal to -1. Well, that means that we can get u1, right? u1 is just the antiderivative of that. It's just -x, right? All right, so that solves u1. Now that we have u1, we can use that to get u2, right? So we can just plug this in up here, right? Plug, well, this one in, plug that one in right there. And so we see that that second equation becomes this. Just this, right? Okay, so that means that u2 prime is just x e to the minus x. And when you take the antiderivative, you get this, okay? So great, we got u1 and we got u2. Okay, so now we have our particular solution because we're just going to plug that in up here, right? So our particular solution is going to be u1 times y1, which was x, right? And then u2 plus u2 times our y2, which was e to the x. Okay, so that's just going to be a minus. Okay, I shouldn't have written a plus there. Okay, it's just this. Okay, so that is our particular solution that we were after. Okay, now how do we find the general solution? Well, we're just going to add constant multiples of this guy. All right. So let's see what happens here. Remember, it's just going to be this guy, and now I'll write this how I meant to do it before with the minus right there, plus a constant times y1 plus another constant times y2. Okay, and maybe I could even write that like this. That's a little bit nicer, right? So here's our general solution. Okay. But wait. I just realized we could do something a little bit better here. Notice that you could factor an x out of these two terms here, right? So this is c1 minus 1 times x, right? I could write this as, I'm putting that one here. I'm going to put these together. So this is plus c1 minus 1 times x, right? But c1 minus 1, if c1 is an arbitrary constant, then c1 minus 1 is an arbitrary constant, right? So what would be even better is to write this in this form. So so let's use b1 and b2, all right? Well, I'll use, yeah, whatever. I'll call that a b1 x, b2 e to the x, yeah. So that would be a better way to do it, all right? They're both correct, but this one's a little bit better because this is a little bit more concise, okay? So that's it there. Okay, so that is, what are we doing here? Variation of parameters. Yes, variation of parameters. Hope you learned something there, and I'll catch you in the next video.